Welcome to Barrio Agham. Magandang hapon mga kabaryo. Ako si Mayor Salvador, isa sa mga tagapagtatag ng organisasyong Pueblo Science. Ang aming organisasyon ay may layuning enganyuhin ang mga bata na mag-aral ng STEM, siyensya, teknolohiya, kaalamang pang-inhinyero at matematika sa pamamagitan ng mga nakakatuwa at nakakamanghang eksperimento. Sabayan niyo po kami linggo-linggo tuwing Martes, alas 3 ng hapon.
Hi, magandang hapon. I'm Jean-Michel Remy Poudreau with the Pueblo Science Team. We are here to provide you with this educational video and we hope you enjoyed it. Sorry about the beard, coronavirus a little bit, you know what I'm saying. But yeah, enjoy the video and yeah. Atoms. They're everywhere. They're in your skin, anything it touches. They're in the air we breathe, the food we eat, and even in that big bright star in the sky we call the sun. Even though we each live our whole lives governed by these tiny specks of matter, we surprisingly have known very little of it for almost all of human history. In fact, it's only been a couple years longer than a century that we were finally able to discern that they have a small center of charge known as the nuclei, along with a set of electrons that reside around it. Join us as we, Pueblo Science, take you on a journey, one that we hope will guide you in teaching particular concepts to your students. Today, we will be looking at the gold foil experiment and recreating it with a few common items that you can find in your household. So stay tuned for collisions and the size of an atom. Our first stop in time is in Manchester, UK, in 1908, a time of revolutionary phenomena were rapidly being discovered and capitalized upon. Folks were being introduced to a handful of consumer products that had never been seen before. For example, cornflakes and instant coffee. The same ones we see today made their premiere onto the shelves of grocery stores everywhere. Air conditioning units that kept them living serendipitously more than ever before began appearing in homes. It wasn't only the industrial sector that was booming though. Scientific advancements were also being expanded at an astounding rate. In fact, 5 years earlier, the Wright brothers had unlocked the secrets of flight, a feat which has transformed the world by providing each one of us the opportunity to fly. Inside a lab at the Victoria University of Manchester, there was something else about to take flight though. Not a person, no. This was an idea. You see, at the time, no one really understood exactly what an atom was. They knew almost everything was made out of these tiny objects, but its structure remained elusive. That is until two PhD students by the names of Hans Geiger and Ernest Marsden were tasked by their supervisor, Ernest Rutherford, the granddaddy of nuclear physics himself, with this incredibly difficult task. Looking fresh there, Mr. Rutherford. Finally, equipped with these two PhD students and some cash money, he devised a method of finally putting an end to the mystery of the atomic structure, his famous gold foil experiment. The experiment consisted of bombarding a small sheet of gold foil with alpha particles, which are positively charged helium nuclei. These alpha particles were emitted from a mixture of radioactive elements contained in a lead box with a small hole. The lead container was necessary as lead blocked alpha particles from passing through and ensured only those alpha particles that were traveling towards the gold foil would escape it. They used this experimental setup to measure the way the particles would scatter, and it detected it with a fluorescent screen coated with zinc sulfide. In 1908, they ran their first series of experiments, and again in 1909, and again in 1910. So what exactly did Geiger, Marsden, and Rutherford find? Well, since most alpha particles were not scattered by the gold foil atoms, it first implied that most of the space inside it was empty. Some would deflect off the foil at small angles, and they concluded such small angle scattering had to be from the Coulombic interactions between the alpha particles and the gold foil atoms. Furthermore, a small fraction of alpha particles would deflect at large angles, which gave Rutherford the last piece of the atom puzzle. It indicated there was a tiny space in the atom that was occupied and would reflect alpha particles that collided with it. Rutherford then published these findings in a 1911 landmark paper wherein he proposed that the atom contains at its center an electrically charged nuclei and electrons surrounding it. If you wanted to do this experiment yourself, well, you're in luck. Although it may be difficult to make a setup as sophisticated as theirs, recreating it with items you can find around your house is as easy as ABC. No, really, we'll show you how. For our experiment, we're going to need cardboard, paper, a few small objects that have flat faces on two sides and one or more faces connecting the two flat faces, such as a cylinder or a box, but any object with these criteria will do. You're also going to need a few small balls about the size of a marble. I was able to find some gumballs lying around my house. Next, we need masking tape, some type of measuring tool, such as a ruler or measuring tape, a pair of scissors, and a pencil. Cool. That looks like all we need to get started. So let's start out with a simple experiment. First, take out your cardboard, and you're going to want to grab your pair of scissors and cut out a circle that is at least twice as long as your objects. These cardboard circle cutouts will be used to conceal the objects you have gathered. We needed the objects to have a flat side, as you will be taping these objects to one side of this cardboard circle cutout. It's easy to make a more radially symmetric circle if you draw it out on the cardboard first. Yeah, that's a good looking circle. Next, take your tape and make a roll. Place your roll onto your cardboard and place the object on top and apply force with your palms to ensure that the tape is stuck on both the cardboard and the object. Now, grab a ball or two, and let's set up our first experiment as follows. Take some paper and tile as many as you need to have a large surface area. It should fit you inside of it. We will be placing the cardboard cutouts with our objects underneath on this paper floor. Finally, have another person take one of the balls and start rolling them at the object and instruct them to trace out the trajectories of the ball with their pencil on the paper floor. Have them continue doing this in hopes they will be able to guess what the object is underneath with only the information given from the marked trajectories alone. How the balls deflect or scatter off the object should indicate the general shape of the object. Another thing to keep in mind is try to deter them from cheating by peeking at the object. Finally, once they think they know what the object is, confirm their answer with them. If they get it wrong, allow them to continue thinking using the trajectories, or to make more, and if they're close, maybe even give them a hint. That's all there is to it. Once they've guessed the object correctly, swap the object for another that you have, if you have another one available, and restart the process with the other side of the paper sheets. Try not to drop your box like this gentleman though. And you're ready to go again.
We interrupt this program for an important news announcement.
Wow, this is so weird. What is this?
Today, we're gonna be making some oobleck. So go into your kitchen mo and get a big bowl. You're gonna want to get one that can fit your hand inside. Now, you're gonna want to go and look around for some water. Finally, we're gonna need a box or two of cornstarch. The same kind you can get at your nearest SM. Make sure you have an open area that you won't mind getting a little messy like outside, because the cornstarch will almost definitely sumabog once you start pouring it outside the box. Once you're ready and roaring to start, pour the water inside your big bowl until it can easily cover your hand. The more water you use, the more cornstarch you'll need. Now, grab your cornstarch and make sure you tear a big opening in the top of it because you're going to need lots of it. Yeah, that should be big enough. You'll also want to roll up your sleeves. Like I said, things are going to get a little messy out here. Right above your elbows should be good. Finally, start pouring the cornstarch into your bowl of water. Start with an equal amount of cornstarch. Now, mix it up as much as you can with your hands to dissolve the cornstarch.
That's so weird. What the heck?
If the cornstarch is all dissolved and the solution isn't thick yet, continue adding more. Doesn't look like this one's had enough cornstarch, so let's add more and mix it up again. Don't forget to have fun and play around with it.
I can't. What the heck? What the heck? It's like melting when it's not. I'm so confused.
We ran out of cornstarch, so we had to pause and grab a bit more.
A few moments later.
What the heck? Ta-da!
Once you take out the spoon your mom left in the cornstarch box out of the bowl, continue adding and mixing until you're able to take out thick, seemingly solid pieces of what is known as oobleck and watch them liquefy in your hands.
Is it?
What do you mean? Cool, right?
It's like a ball and then it... This is so weird.
Such.
So weird. I'm gonna do this in the summer. I'm just gonna bring my friends out and get buy cornstarch. Look. No, but this is crazy.
This is an example of a non-Newtonian fluid, where the cornstarch formed a network of long chains. Just like a crowded area where one must move slowly through the crowd, the cornstarch solution needs time to change. If a quick force is applied to the cornstarch solution, such as lifting it up and moving it around in your hands, and pressing on it, the network cannot move as quickly, so it stays stiff like a solid. However, when you stop applying force, the solution acts like a liquid again.
Reports as yet. Please stand by for further details. We return you now to your regularly scheduled program.
For this next experiment, we're going to be building a sort of makeshift bowling lane from the materials we gathered earlier from around the house to indirectly measure the size of one of our balls, just like Rutherford did with the size of an atom. Make sure you're in an open area with lots of room to walk around in. Get out your measuring tape and measure out two 50cm strips of masking tape. Now tape one of those strips to the floor. We will call this the rolling line. Its role is as our alpha particle emitter. Next, use your measuring tool to measure 100 centimeters away from the rolling line you had just created. You'll want to have this measurement along the short side of the rolling line, or perpendicular to it. At the 100 centimeter mark, you'll want to place another piece of tape. We will call this the field line. It will act as our gold foil and has a chance of deflecting our simulated alpha particle. Next, grab 6 or 7 balls. These will act as our alpha particle as well as our gold nuclei in the gold foil. Now, find your tape and scissors, because we'll need to cut a few more strips of masking tape, but smaller this time around. Start cutting strips that can fit over your balls and stick them to the floor. You're going to want 5 of these small strips. It's easier if you're working with other individuals as well, because all these parts can be carried out at the same time. Once you have all your tape, measure out 5 centimeters from the end of the field line and make a marking at this 5 centimeter line with your pencil. Grab a ball and place it on the marking. Tape it down using one of the smaller strips of tape you or your partner prepared. Next, you're going to repeat this, but with 10 centimeters instead. So take your measuring tape again and measure out 10 centimeters from the first mark you made and make another marking. This mark should be 15 centimeters from the end of your field line. Once you mark 10 centimeters from the last mark, tape another ball down at the spot. Now do this again for a mark at 25 centimeters, 35 centimeters, and 45 centimeters from the end of your field line. You'll want to tape all of them down so they are stuck in place pretty well. These balls on the field line will act as atoms in your gold foil. Fantastic! With your remaining ball and some paper to write some observations down for this experiment, it looks like you're ready to start. Start rolling your ball from the rolling line to the field line without any intentional aim. That is, roll it without trying to hit one of the balls or none. Try to use random directions from and starting locations on the rolling line. You'll want to record a tally for every instance that one of your balls you rolled collided with a ball on the field line. Get comfortable, as you'll need to roll the ball 50 times or more to get accurate results. Make sure you're rolling on the rolling line and aren't throwing balls in directions that are outside the field line. Continue the experiment until you rolled it at least 50 times and make sure to record every single hit. If done correctly, this experiment should capture the essence of what Rutherford did with his experiment. After we've gathered our data, we will be mathematically analyzing it using probability, so make sure you get ready and you have your brain prepped for that. Once you've rolled the ball 50 times or more, we'll need to analyze our data. Hold on a minute. Before we analyze the results, we should clean up like every good scientist would do and remove the tape off the floor and balls. Now, let's recap what we did in this experiment. We rolled our balls, or alpha particles, from a rolling line towards 5 other balls placed 100 centimeters away at a field line. These 5 balls were arranged not so differently than the way nuclei would be in a sheet of gold foil. If our rolls were truly random, then the probability that one of the balls we rolled collided with one of the 5 balls should be equal to the ratio of the field line blocked. So how would we go about determining the ratio of the field line blocked? Well, we know that a circle has a radius which we'll call r. The condition for a collision to happen then is that the distance between the centers of the rolling ball and each and every field line ball is equal to 2 times the radius when the rolling ball is placed along the same axis as the field line balls. Here we can see them lined up vertically. Furthermore, the rolling ball can be flanked from either side on this axis, so we need to multiply our result by 2. Lastly, we know we have 5 balls on our field line, so we will need to multiply this by 5. If we substitute 2 times the radius for the diameter, there's something special that happens. We now have a way of calculating the diameter of our balls, or our nuclei, just like Rutherford. So let's go ahead and rearrange the formula for the diameter. Here, we can see the diameter is equal to the field width multiplied by the number of hits divided by the number of rolls, and all of that divided by 2 and the number of targets. One thing we should ask ourselves is, do we have all the necessary variables to calculate this already? Let's check. Do we have our field line width? Yeah, we chose that to be 50 centimeters. We also recorded the number of hits and rolls made, so we have those. We know we used 5 balls, so we know that the number of targets has to be 5. And with that, we should be able to calculate the diameter of our ball. Here's the data I had when I did this experiment the other day with my gumballs. Using the data from running this experiment and the formula above, I was able to acquire a diameter size of 2.3 centimeters. We can see how correct we are by measuring the balls directly. My gumballs were actually 2.5 centimeters. Wow, how cool is that? We were able to figure out the size of our balls indirectly using clever mathematical tricks and some elbow grease. I believe the words you're looking for are, "That is very cool." Anyways, thank you for tuning in. We at Pueblo hope you enjoyed and will have a fun time playing and learning from these experiments with your students. Have a great evening and see you again soon. Bye. Enjoy our experiments and want to earn some extra cash? Pueblo Science is starting its collab program and offering money through Gcash if you show us how you do it. Here are the mechanics. Recreate one of our featured experiments in this episode by making a photo collage or a 1-minute video. Be as creative as you can. Each Facebook account is allowed to submit a maximum of 1 entry per experiment only. This account should have liked the Pueblo Science Philippines Facebook group. Post your photo or video on the comments section of our Facebook Live post. By joining the contest, you have given Pueblo Science Philippines the rights to use your photo or video along with the name of the participant for various publications and other purposes. Deadline of submission is this Friday, so make sure to mark it in your planner. 5 lucky winners will be selected per episode, and their entries will be featured in our page. They will each receive 100 Philippine pesos worth of Gcash load. Winners will be messaged through Messenger to get their details.